With low Earth orbit harnessed, it's time to look further afield. To build a spacecraft and rocket system to reach Mars is a mammoth undertaking, but if successful, it will return the United States to the top of the space achievement ladder. The first requirement? A space capsule able to carry 6 astronauts for a long period of time and return them safely to Earth. Orion is its name, and it has flown once already in a shakedown. The next flight will be an unmanned test mission past the Moon, followed by a third manned mission. The components for the vehicle are developed around the country, tested and checked, then passed on for assembly. The minutest bolt and circuit is designed, tested, redesigned and tested again. Slowly the systems come together with the aid of some breakthrough technology, particularly in manufacturing methods, new materials and processes. The first thing to notice is that NASA have gone back to the classic conic shape like Apollo, the safest design yet devised. Avionics, control systems, computer software and a glass cockpit, all state-of-the-art.
And the concept was to go with a glass cockpit, and what that means is that the instruments are all images on a computer screen. They are all on the glass, so rather than flipping a physical switch, the crew brings up a computer screen and flips a virtual switch, a little icon of a switch or icon of a valve. And with the exception of 7 panels right around the computer screens, which have about 60 switches, that is all of the cockpit of Orion happens on the glass. One big benefit is a weight savings because you don't have to have a physical switch. And having a physical switch, not only is there the weight of the switch, but you also have the weight of the wire to the switch. And you have to have the weight of circuitry that takes that wire and feeds it into the vehicle computers.
Because of Orion's size, its all-important heat shield is the largest one ever made, and new processes were required to manufacture it.
The Orion heat shield has got to be able to withstand landing loads on the order of 300 to 400,000 pounds. Because we're returning potentially from the Moon or beyond, and the flight duration from the time in which you commit to a return to the time you actually land, the weather conditions on Earth can be substantially different or difficult to predict. And so the Orion spacecraft has to be able to land in the ocean in a wide range of sea conditions, wave height, wave slope angle, and horizontal winds. That is what's driven us to a skin stringer architecture that utilizes a thick laminate composite skin bolted to a titanium substructure.
We bond on an ablator called the AVCoat. The ablator is the thermal protection part of the heat shield. The very outside of the ablator actually gets hot enough that it decomposes, and that's the ablation part of it as opposed to an insulator like a shuttle tile.
Then come the ancillary structures and equipment that will ride with the capsule. The escape tower, designed and tested, will pull the capsule away from the main rocket in the case of an emergency. Adapter separation from the rocket's upper stage. Parachute deployment. The connecting adapter to the EMS. The EMS is the service module attached to the Orion in flight, supplying oxygen, water, power and heating. Built by ESA, it is based on their very successful ATV program, which delivered supplies to the ISS. It will also provide the main engine thrust for deep space maneuvering.
We have, in particular, very tight schedule in front of us. So everybody's working under a high pressure to meet the dates, and this requires a very close collaboration.
I see a very motivated team, and so far as an agency we are quite happy with the performance of the European industry.
The US Navy is tasked with retrieving the capsule from the ocean. At first they train in the pool, then calm waters, then the Pacific, and finally the real thing. Experts continue to evolve the process and training in readiness for the day when a manned flight returns from deep space. This is the RS-25, the Ferrari of liquid rocket engines and the main engine from the Space Shuttle program. Economically repurposed for the Space Launch System, 4 of these engines will power the main stage of the rocket. The main solid rocket boosters of the shuttle program also have a renewed life in the SLS. With another 2 segments added, the boosters will thrust for over 2 minutes.
This project has been a real fun effort in trying to take a heritage booster that had many, many years of reliability and great performance and evolve it into something bigger and better.
When we first undertook this design and qualification for the new booster, part of the mission was to make the booster more affordable and more modern, and of course it had to be completely redesigned for a new mission. It's a larger booster, and the mission profile is sufficiently different to where pretty much everything on the inside of the booster is different. There's well over 1,000 individual processes. Working with our customer, we were able to identify several hundred areas of improvement.
We've got totally new avionics on this vehicle versus what we had on shuttle. It's state-of-the-art.
Bigger and more powerful than any previous launch system, the SLS has been under development for some time. Designing it is one thing, building it another. In new or refurbished factories and assembly shops, the body of the largest rocket ever to fly is being constructed one piece at a time. The massive hydrogen tank takes shape. The smaller oxygen tank soon follows. The interim stage for the manned flight is another hydrogen-oxygen motor supplied by cryotanks, fabricated with new technologies.
So to design and manufacture this tank, we use new materials. We process the tank by automated fiber placement. The benefit of that is we can lay down the material quickly, which provides us a low-cost operation and a very lightweight tank.
We've worked on this program for 29 months, and when we started, we'd never built a tank of this size by the methods that we did. We did automated fiber placement and fluted core, just developing the robotic fiber placement equipment and way to make the skirt in one piece was a large challenge.
Each exacting piece is fabricated, test articles are run through the mill, vibration tests, vacuum tests, acoustic tests, stress tests. Nothing is left to chance. new technology and new materials for a new generation of space exploration.
So this test, there were several things that we looked at. This was the first time we used those thermal knives to start the deployment sequence, and that allowed, cut some tethers that then allowed the solar array to deploy. We wanted to test the locking mechanisms to ensure that it locked properly in space, because anything that could possibly go wrong, we wanted to see test down here so that we can ensure a successful flight.
It's all about technology. If you don't develop technologies for the future, you won't go where you want to go. So composites will decrease the weight of the tanks. It'll increase the payload performance of the launch vehicle. It'll give us, it basically enables things that we don't have today.
Soon the mighty rocket will lift human beings up further than ever before. The flight to Mars will be a long one, too long for a crew to sit in a capsule. Habitat and supplies will also be lifted to orbit and assembled. Several companies have been selected by NASA to carry out studies for a suitable system to do the job. A bit of competition is always good for invention. Bigelow Aerospace, with its Expandable Activity Module, or BEAM, currently being tested on the ISS, will develop and test a prototype of X-Base, a 330 cubic meter expandable habitat. Boeing of Houston is developing a modular habitat system that leverages more than 15 years' experience in designing, developing, assembling on orbit, and safely operating the International Space Station. Lockheed Martin will refurbish a multi-purpose logistics module into a full-scale habitat prototype that will include integrated avionics and ECLSS. Orbital ATK will mature the mission architecture and design of their initial cislunar habitat concept based on the Cygnus spacecraft that now supplies the ISS. Sierra Nevada Corporation's space systems will study and refine a flexible architecture and concept of operations for a deep space habitat that draws on the lessons of 3 to 4 commercial launches to construct a modular, long-duration habitat. NanoRacks, in conjunction with its partners, Space Systems Loral and the United Launch Alliance, referred to collectively as the Ixion team, will conduct a comprehensive feasibility study regarding the conversion of an existing launch vehicle's upper stage, or propellant segment, into a pressurized habitable volume in space.
So if you're designing spacecraft to be in the Mars orbit, then the studies we're doing on Space Station can be applied and help us design more durable spacecraft for that Martian atmosphere. MISSE stands for the Materials International Space Station Experiment. We do study the durability of polymers in terms of their mechanical properties with radiation exposure. And we hear a lot about the radiation exposure impact on humans for flights to, say, Mars. But polymers and other materials that are used on spacecraft can also do great from radiation, and that's one of the things I study. The MISSE 8 experiments do take a little bit of time because we do very careful dehydration measurements of the samples after they've been in space. What we found is that the Teflon erosion rate is highly dependent on the amount of sunlight and possibly the heating too. you need to know which of these environments it's going to be exposed to because it'll erode at a different rate depending on the environment.
Assembling spacecraft in orbit and fueling them for the long journey to Mars sounds simple enough. On-orbit refueling is anything but simple. NASA have been developing a system for unmanned refueling for quite some time and have a test article on board the ISS.
We can take a pick-and-place robot, put the tool wherever we need it to be, and all it needs to do is drive that tool because the smarts are in the tool. So that's what we learned from working on Hubble, is you put a smart tool with the astronauts and accomplish, both things. You've got smart tools and astronauts working together. Now we're putting smart tools with robots and trying to accomplish the same type of things we did on Hubble.
Aimed at developing capabilities for servicing, even refueling spacecraft on orbit, RRM is like doing precise surgery at a distance, doctor and patient separated by the void and vacuum of space. It's tough, but the payoff is huge.
Robotics can do things that humans can't do in terms of precision, in terms of control, holding a particular spot for 6 hours while engineers on the ground debate what to do. We can't ask a human to do that.
The robot is a very stiff, rigid interface. It's not forgiving like an astronaut's hand. So we have to take that into account. When you push on something really hard with the robot, you build up really large contact forces. When the astronaut pushes on something, his wrist might give. He's got his own internal sort of software compliance running. But in order to accommodate the robot so we don't break anything, we have to build features into the tool, features into the software. Just getting the robot to go where you want it to go, and, they don't position precisely. So you have to do things like build lead-in into the tool. An astronaut could probably just get it right on there because he's right there. So we do have to do things to make them, very specific to robotic operation.
That task successful? Next stop, Mars. The first manned mission to Mars will probably only orbit the planet, checking out all the gear and processes, even launching communication satellites, and finalizing landing sites in preparation for the next mission, which will then make the descent to the surface. And that has a whole new set of problems to overcome. Unlike the Moon, Mars has stronger gravity, about 0.6 of Earth's, but it does have an atmosphere where parachutes can be used, although the atmosphere is very thin and not very deep.
Well, it's a funny thing about Mars, but if you take the average of the planet, the average height of everything in the planet, it turns out that most of the north is 2 kilometers below that, and most of the south is 2 kilometers above that. And it's just, we always land in the north because there's a lot more atmosphere. If we land in the south, it's like 4 kilometers less of air to come to a stop. In fact, at the altitude of the mountains in the south, the Mars Science Laboratory was still supersonic as it was descending into the crater that it was reaching in the north.
Assuming the need to pre-position habitats, supplies and equipment on the surface prior to a human landing, NASA and its partners are looking at several solutions. One is the HIAD, or Hypersonic Inflatable Aerodynamic Decelerator. This is basically a very large inflatable heat shield, much larger in area than the payload, able to slow the craft considerably faster than a standard spacecraft heat shield. Plans are to test the system on a payload from the ISS, utilizing a Cygnus resupply spacecraft. Once lower in the atmosphere, parachutes will further slow the payload to an altitude low enough for rocket engines to take over. Morpheus and the Zombie flight systems have matured over the last few years and are capable of delivering cargo to a planet's surface autonomously, avoiding rough terrain or other obstacles without human intervention. Adding yet another building block to our human effort to explore the solar system.